Yeah, dear students, today our topic is electric flux. In electric charges and fields, we are having the continuation topic is electric flux. Now, in this session, I am going to teach you electric flux topic. Right? What is the electric flux? Now, by the definition, electric flux over a given surface is total number of electric field lines passing normally through the surface area. Passing normally through the surface area. Now, this one is called here electric flux. Sir, electric flux is denoted by which letter? That means to represent the electric flux, there is a representation, denotion. One letter is there. The letter is nothing but here phi. Now, phi is the denotion of electric flux. Thereafter, sir, suppose if you want to understand the electric flux means, first you have to know the area. Sir, what is the area? Area, is it a vector or scalar? Last year in first PUC, when I am teaching you motion in plane chapter, in that in vectors I have told you area is a vector quantity. That means we have to know, sir, area is a vector quantity. Small area is a vector. Small area is a vector quantity means, that small area is having both magnitude as well as direction. Now, let me see here, what is the area vector direction? Now, if you take area vector, if you take any surface of the body, now that any surface of the body, is having what type of direction of area vector? Now, for example, here I am going to take, this is nothing but one area of cross section. Here I am taking. Now, this is the area of cross section. Sir, for this area of cross section, here one area of cross section I am taking. Here another area of surface, that means cross section I am taking. Sir, two are there. Now, for these two, what is the direction of area vector means? Now, this is the area, one of the area, and this is nothing but another area. If you just take, here I am giving one more example. Right now, this is one surface of body I am taking. Now, sir, for this surface of, this is, length is there for this surface and breadth is there. Sir, length, breadth both are there. So, this surface is having the area. Sir, here you just see one more example I am taking here. What is that one more example means? Right, another surface of area. I am going to take here. Now, this is nothing but another surface of area I am taking. This is another surface of area. Now, this is in one direction surface is there, in another direction surface is there. Here one surface area is there, and here also one surface area is there. Right, sir, for all these areas, in different cases I am taking, this is one first day example, this is one second day example, and this one is nothing but third example, and this one is nothing but, fourth examples. I am giving here 4 examples, right? In these 4 examples, sir, what is the direction of area vector? Means, first of all, you take it here, right? Now, always for a area, the direction of the vector, the direction of the area vector is normal to the surface. For example, this is this surface. Now, for this surface, area vector direction is nothing but normal to this surface. That means normal to this surface means perpendicular to this surface. Right, here if you take, for this surface area, this area of cross section, the direction of area vector is nothing but normal. That means like this we can take. Now, this is nothing but area vector direction, and here area vector direction. Now, for this one, the direction of the area vector is nothing but how we can take it as means, we can take it as like this. Area vector direction is normal to this surface. That means for this surface area, normal we have to take. Now, this one is nothing but another one. Now, for this one, normal to this surface. Now, the area of the direction of the area vector, we can take it as like this. Now, dear students, you just observe here, whatever it may be this surface area. Now, for that surface area, direction of the area is nothing but always perpendicular to the surface. Now this complete board is there. Now for this complete board, what is the direction of the area? That means this board is nothing but is having the length as well as breadth. So this complete area of the board. For this area of the board, the direction is nothing but normal to the surface. That means complete to the surface, the direction of the area vector is normal to the surface. That means towards you people. There is a direction of the vector. Right, here I am having few examples. With the examples I will explain to you. Now, first of all, you take it here. Now, this is one book I am taking. Now, you are observing this is the book. Now, sir, this is the, length is there, breadth is there for this book. So, area, this is the area of the book. Sir, for this book, what is the direction of area vector means? The direction of area vector is normal to the surface. See, with a pen I am showing the direction. Right now, this is the direction of the area vector. Suppose if the area, if you place it like this, if the surface of the book, if you place it like this, then what is the direction of the area vector means? For this surface, perpendicularly, upward direction like this. Suppose if the face, you rotate it like this, Sir, after rotating like this, what is the area vector means? Downward direction like this. Now, for this surface, the area vector is nothing but we can take towards this direction. That means leftward direction like this. For me left, for you I think so it is right. Now this is the direction. That means area is a vector quantity. Small areas can be considered as vector quantities. Its direction always normal to the surface. Sir, you have told whether it is like this, like this, like this, and like this. In 4 cases, like this. This is in first case, this is the direction of area vector. In second case, this is the direction of area vector. In third case, this is the direction of area vector, and other case, this is the direction of area vector. Suppose, sir, if it is like this, suppose if the surface is tilted like this, then what is the direction of area vector means? The direction of the area vector also tilted little bit from actual one. Just to remember this one, area is a vector quantity. The direction of the area vector is always normal to the surface, area. Whatever the surface you are having, for that surface, this is nothing but normal. Now, I think so you got the idea, right? Any doubts, you just ask me later. Now, area is a vector quantity for whatever it may be. The vector area is a vector quantity for whatever the surface. Now this surface is for this surface, area vector is perpendicular to this surface, or this direction. Now for this surface, in this direction, for this surface, in this direction, for this surface, upward direction. Of course, you may take it as downward also, no problem. Right. Now thereafter, sir, after having the area vector, now let's come to the point of, which is nothing but here, electric flux. Sir, electric flux is nothing but total number of electric field lines passing normally through this surface area. Right. In one surface area, if number of electric field lines are passing means, those total number of lines together called here electric flux. I will show how. Now just to take it here, now this is nothing but a area of the surface. This is the area of the surface. Now this area, what is the direction of the area vector? Direction of the area vector is nothing but delta S. I can take it as like this. Now delta S, S is represents area, or area can be represented with a letter also. Now we just look at here, total number of electric field lines. Electric field lines means actually electric field can be represented in the form of lines. Those are said to be electric field lines. Right, you just see electric field can be represented in the form of electric field lines. You just see here. Now this one is nothing but one of the electric field line. Now this one is nothing but another electric field line. Now another electric field line like this. I am taking another electric field line. Right, it is entering into the surface and coming out from this surface. And here I am going to take one more electric field lines. This electric field line entering into this surface and electric field line coming out from this surface like this. Right, here I am going to take one more electric field line entering into this surface and coming out from this surface. Right, here I am going to take one more electric field line entering into this surface and coming out from this surface. Here also another electric field line is there. Now like this I have taken. Now we just see to that. Okay, these all are nothing but electric field lines. Electric field lines can be visually represented with lines. These lines are maybe straight or curved also. In previous classes already I have explained about it. Right, now here you just see, okay, in the electric field, that means electric field lines are, how many electric field lines are there? Some number of electric field lines are there here. Right, electric field is denoted by which letter? Means capital E bar. Okay, here I am representing capital E bar. Okay, like this. Now here totally how many number of electric field lines are there? Means 6 are there. 1, 2, 3, 4, 5, 6. Among these 6, only 5 lines are entering into the surface and coming out from this surface. Sir, how many number of electric field lines are passing through this surface area? Those number of electric field lines are called here electric flux. That means the number of electric field lines which are passing through this surface area. Okay, now those are number of electric field lines all together here called electric flux. For example, okay, generally we know that ladies or girls. If you just see here, if you just look at here, now you are observing, okay, one ring I am taking here, one rubber band I am taking. Okay, this rubber band is having the surface area. Now this hole is completely, it becomes area, surface area. One area is there. Now generally ladies, those are having the short hairs. Okay, to make them to long hairs, the people used to use one kind of object. I don't know exactly what it is called in Kannada. Right, in this one, see here hairs are there. Every hair, if you just consider one electric field line. In this case, if you just see, okay, here how many number of hairs are passing through this rubber band? Okay, these total number of, see how many number of hairs are passing through the rubber band. Okay, these complete hairs are considered as hair flux. Right, if electric field lines means electric flux. See, in this case, less number of hairs are passing here, so we can consider flux is less. Suppose if the total hairs are passing through the rubber band, total hairs are passing through the rubber band like this, in that case what we can tell? Flux is more. Right, sir, when the flux is more means more number of electric field lines are passing through the surface area, in that case we can tell flux is more. If less are passing means electric field is nothing but less. Here less number of electric field lines are passing through the area. Okay, less electric flux can be considered. If here more number of electric field lines are passing means we can tell more flux. Right, here, okay, totally this first line and this last electric field lines are not passing through the area. Because of them, okay, they both are not considered as a electric flux. Okay, remaining whatever 4 lines are passing through the unit area, they may be considered as electric flux. And thereafter, sir, electric flux, how it is going to change? Sir, suppose if the area vector direction is changing, electric flux also is going to changing. Of course, it is going to changing. For example, this area I am going to tilt it little bit like this. Okay, in this case you just see, okay, delta S bar is nothing but area vector, E bar is nothing but electric field. Yeah, here area vector and electric field both are in same direction. So here angle between, okay, electric field and area vector is nothing but 0 degree. That means angle between the electric field and area vector is nothing but 0. Why? Because both vectors are in same direction. If both vectors are in same direction means, okay, those are parallel vectors. For parallel vectors, electric angle is 0. Now, if you see in next case, see this one is going to tilted like this. Now this one is going to tilted like this. Now this is the area vector, and this area vector has tilted a little bit like this. If you just see, I am going to tilt it a little bit more. Okay, right. Alright, now same area vector I am taking here, area of cross section I am taking. Now for this area of cross section, the direction of the area vector, we can take it as like this. Normal to this surface, we can take it as like this, delta S bar. Now in that case, electric field vectors, electric field lines, if you just see once again, I am going to draw electric field lines. Now this is first one, and this one is nothing but second one, and this one is nothing but third one. Third electric field line is passing through here, and this one is nothing but fourth line, and this one is nothing but fifth line. Like this. That means in that case, if you just see here, sir, when here you just look at here. Now this is nothing but direction of electric field here. Now this is the direction of electric field. Direction of electric field is nothing but E bar, and this one is nothing but area vector. Sir, in these two between there is an angle. That angle is nothing but theta here. Angle is theta. Sir, between this electric field direction and this area vector, the angle is nothing but here theta. Right? Because of this, sir, if you rotate the area vector little bit from the direction of electric field, in this case, number of lines passing through the area decreases. That means compared to first case, in second case, here what we are observing means flux is smaller. Suppose here I am going to take one third case. In this third case, what I am observing here means, this is nothing but one area vector I am taking completely. This is one area vector. Area vector is completely rotated, to 90 degrees. Now in that case, sir, what is the direction of area vector means? Direction of area vector is nothing but delta S bar. This is the direction of area vector. Now you take it, the number of electric field lines are nothing but 1, 2, 3, 4, 5, and so on. We can take it. How many you can take? Sir, in this case, you are observing or not? In first case, 4 number of lines are passing through. In second case, 2 number of electric field lines are passing through the area. In last case, no one electric field line is passing through the area. Sir, in this case, the direction of the electric field, E bar here. Now here, this one is nothing but E bar. Now this is the direction of electric field. Sir, in this case, in between these two, the angle is nothing but how much is there means 90 degree. That means in that case what happened means electric flux is nothing but 0. Electric flux is 0. Why? Because no one electric field line is passes through the area. That means here, sir, when the values, if the angle is increases between electric field and area vector increases, if the flux is decreases means when it is possible means only if you take it cos function, right? If you just look at here, now electric flux mathematically how it can be written as means, right? You just see here, mathematically electric flux can be written as flux phi is equal to E bar dot A bar. A bar is nothing but, we can take it as A bar is nothing but area vector, E bar is nothing but electric field. Of course, delta S also we can take, right? If you want, you take it here delta S bar also, delta S. If it is delta means flux also delta, small value we can consider, right? Sir, dot product of electric field and area vector is gives rise to here electric flux. Now this one we can write it as electric flux is equal to, we can write E into delta S cos theta. Why? Because means, if the cos value will becomes increases from 0 to 90, from 0 to 90 cos value is going to decreases, right? Here theta value is increases, in that case flux is decreases. So now this one is nothing but mathematical expression for electric flux. You just see here mathematical expression for electric flux. Electric flux can be defined as the dot product of electric field and area vector also. Right. Now dot product of two vectors is nothing but a scalar quantity. That's why here, okay, what I am going to tell means flux, electric flux, it can be is a scalar. Electric flux is a scalar quantity also. It is a scalar quantity. That means electric flux is not having any direction, it is having only the magnitude. Why? Because means here you just see here total number. Number is nothing but a value. Value is nothing but a scalar quantity. So electric flux is a scalar quantity. And thereafter, sir, what is the SI unit? Okay, its SI unit is, sir, what is the SI unit? SI unit. It's a SI unit. Okay, is, sir, what is the SI unit of flux? Okay, let me see here. For electric field, SI unit is, anybody just to remember? For electric flux, for electric field, SI unit is Newton per coulomb. Newton per coulomb. Right. Now this one is nothing but area vector. For area vector, unit is nothing but meter square. So SI unit of electric flux is nothing but what we can take it as means, we can take it as Newton meter square per coulomb. That means in simply R over R, how I can write? I can write Newton meter square coulomb inverse. Coulomb is the unit of charge. Now this is nothing but electric flux. Once again, electric flux over a surface is total number of electric field lines passing normally through the surface area. Right now, normally passing. Suppose if the area vector direction is changing from the direction of electric field, electric flux will becomes decreases. Right. In last class, no one electric field is passing through the area, because of that electric flux is 0. Right. Here I would like to tell one more thing. Okay. In next session we just to continue. Right. We just to take one note in your notebook. Yeah, dear students, after having the electric flux, now the topic is nothing but continuous charge distribution. Now, what is the necessity to study this topic means, I will tell you that very first one. We know that in practical, charge on a body is very large. In practical, charge on a body is very large. But charge of electron is very small. Sir, what is the charge of electron? Sir, electron charge value, charge of electron is nothing but, the value is nothing but 1.6 into 10 power minus 19 coulomb. Now this is nothing but very small amount. Right? Charge of electron is very small, but charge on a body is, in practical, it is very large quantity. Because of that, the addition of charge or removal of charge from a body is nothing but, that is, it can be ignored. For example, here one charged body is there. Now this is a charged body, right? Now this is a charged body means, if you take it whether it is positive charge or negative charge, whatever it may be, charge is there. Now in that case, on this body, that means for this body, from this body, if you add some electrons or remove electrons, that means from this body, if you remove some electrons, if you add some electrons, that is ignored in this case. Why? Because means charge of electron is very small. That means, in this case, whatever the charge is locating on this body, this charge is continuous. That means addition or removal of electrons, from this body is completely ignored, because of whatever the effect is existing here on adding the electrons on removing the electrons from this body, okay, whatever the effect is existing, that effect is completely ignoring. Because of that, okay, here charge whatever located on body, the charge is nothing but here continuous on this body. So continuous charge distribution. That means on charge on a body, by considering the charge on a any dimension of body here, okay, we are going to study continuous charge distribution as a linear density of charge, surface density of charge, and volume density of charge. For example, here one body is there. Now this is a body, right? This is a linear body I am having, right? Now this linear body, if you give the charge, means, okay, the charge is completely resides on the outer surface of the body, right? Sir, what is the length of this linear body? Means length of this linear body is nothing but I can take it as L. Now for L length, how much amount of charge you are giving? Means, okay, Q amount of charge you are giving, right? If you take the ratio of charge to length, means that gives rise to here linear density of charge. That means linear density of charge is nothing but, how I can write, means linear density of charge is charge per unit length, or length also you can take it as charge per unit length, right? Now it is denoted by which letter? Means it is denoted by a letter that is nothing but lambda, okay, right? Here linear density of charge, lambda equal to, I can take it as here, okay, charge per unit length. This is the charge per unit length. Now we know that, sir, what is the unit for linear density of charge? Lambda. Means for this unit is nothing but it's a unit is linear density of charge, unit is Q is nothing but charge. For charge, unit is coulomb, right? Now for this one, meter. So coulomb per meter we can take, otherwise, okay, R we can take it as coulomb meter inverse, right? Don't think this is the centimeter inverse, okay, this is the coulomb meter inverse. So capital C I am taking here, so coulomb meter inverse. Now this is nothing but linear charge density. Afterwards, surface charge density. For example, if you take one area, now this is one body I am taking, this body is having the area, length is there, breadth is there, so area is there. Now whatever the charge if you give to this body, means the charge is resides on the outer surface of the body like this. Now how much amount of charge we are giving here? Q amount of charge we are giving, right? To which we are giving the Q amount of charge? We are giving the Q amount of charge to a area. Now in that case, okay, charge per unit area can be considered as here, okay, surface charge density, which is denoted by sigma. That means here surface charge density is nothing but, right here I am writing, it is charge per area, charge per unit area is nothing but here, okay, surface density of charge. Sir, it is denoted by which letter? Sigma. Sigma equal to charge per unit area. Of course, we can take it as like this. Okay, right. Sir, what is the unit of surface charge density? Means unit of surface charge density is nothing but, right, it's a unit is nothing but, unit is for charge, which is nothing but coulomb and meter square. Okay, otherwise we can write capital C is nothing but coulomb meter square inverse. Now this is nothing but unit for surface charge density. And volume density of charge, if you just to see here, now I am going to take one sphere here. Now solid sphere I am taking. Now solid sphere means completely it is having a matter within it. One solid sphere I am taking just like a cork ball. Okay. Now in this one, suppose sir this solid sphere is having volumes are here, volume, right? If you give the charge to this one means charge is completely resides on the outer surface, completely resides on the outer surface of the volume. Now because of this, how much amount of charge we are giving? Q amount of charge we are giving. So here volume charge density is nothing but it is charge per volume. Charge per volume, unit volume. Charge per unit volume on a body is nothing but here. Charge per unit volume on a body is nothing but here. Volume density of charge per unit area is nothing but surface density of charge. Here if you just look at here, charge per unit length is nothing but here. We can take it as linear density of charge. Sir, here volume density of charge is denoted by which letter? Means that is nothing but rho. Rho is equal to, that means volume density of charge. Rho is equal to, we can write charge by volume. We can write charge by volume. Right? Now like this. Sir, what is the formula? That means what is the SI unit for volume density of charge? Means unit is nothing but, right, just to see here, unit is, let's see, unit is for charge, that is nothing but coulomb, for volume, that is nothing but meter cube. Okay, here I am going to write coulomb meter power minus 3, that means Q, inverse Q. Coulomb meter inverse Q is nothing but unit of volume density. Now this is the topic, 2 topics in this session I have completed. Now see here, ma dear students, after a long time I have began the topic. There is nothing but electric flux, and thereafter continuous charge distribution. In my home itself only I have made a blackboard in my native place. Because of that some lagging is went on, but whatever it may be situation, today onwards I am going to put the videos continuously. And if you have any more doubts, first you bring to my notice. Why? Because means whatever the doubts are rising in my teaching, you bring to my notice itself only. I am going to clarify them. Yes?